Thank you. Okay, let's get started. It's a great honor to have Professor Volker Springel here to give us a great lecture. Sure. Volker got his PhD in astrophysics at the University of Munich in 1999. And then he went to Harvard as a postdoc, and then joined Heidelberg faculty. Right now, he is the director at the Max Planck Institute for Astrophysics, MPA. He had received many honors, and but only the ones with a lot of money. Okay, so in 2020, he received the Global Cosmological Prize, which I think has more money than the Nobel Prize. He is the creator of the very famous, the most quoted simulation in history of astrophysics. He's the main architect. He has many other contributions, so it's a great honor. Let's welcome Professor Springel.
Thanks, Renyu. Yeah, it's also an honor for me to be here. Fantastic, very brand new university. I'm very impressed. And I would like to, this afternoon, tell you a little bit about my work in cosmic structure formation. I would like to tell you a bit about the universe, how we think galaxies form in particular, and also, how we do that from a theoretical point of view, and also, discuss a few of the open questions as well as some of the successes. And I would like to start this out discussing a bit dark matter, which is this unknown material, of course, that dominates the matter content of the universe. Tell you a little bit about what we've learned about that, primarily also through simulations, actually. And I will then discuss the problem of doing so-called hydrodynamical simulations in cosmology. They have the aim to form, well, the things we actually see, right? The galaxies around us. And they are kind of like the line posts in the universe. And then I would like to discuss a little bit also how we nowadays try to interface cosmology and the field of galaxy formation, because we're currently working on the problem of trying to understand what the real cosmological parameters are, and basically trying to find cracks in the standard cosmological model. I see there's a message popping up. Should I click on what should I click here? The white one. Okay. Yeah, unfortunately, I'm not sure. So it's probably streamed. Okay, we'll see. Bear with me. We just installed the streaming application a second ago. So, so this type of picture, at least the astrophysicists among you will have seen, right? We know a lot about the universe primarily from the so-called microwave background radiation that you see here on the left. This is a thermal heat bath that reaches us uniformly from all directions. It's literally the remaining heat of the hot Big Bang. And it's now cooled down to 2.73 Kelvin above absolute zero. So it's not exactly hot anymore, rather it's extremely cold. But it still has a Planckian spectrum, very much so, except that there are tiny ripples that you see here in this left map, which only have an amplitude of 1 of 10,000 around the mean temperature. And we see that these ripples in this heat bath at a time where the universe was 380,000 years old. So it's really way back in the past. And in fact, this is one of the earliest observations that we have. And it tells us a lot, because it tells us how the universe looked like at that time. This sets the initial conditions for everything that happens later. And a sketch for what happens later you see here on the right, including the microwave background fluctuations. We don't know what caused the Big Bang in the first place. We know it happened. The universe is extremely dense, expanded rapidly at this early time. And expansion slowed down because of gravity. The gravity pulls together the material, it slows it down. But about 5 billion years ago, the cosmic extension has accelerated. And that's caused by some kind of anti-gravity, which we call dark energy. So these are, of course, important puzzles. And it's a fairly strange conjecture that the universe is made up of actually dark energy as well as dark matter. And we have these observations of the microwave background. They tell us a lot about the initial conditions as well as about the composition of the universe, because we can theoretically predict how these fluctuations in the microwave background arise in inflationary cosmology, and how these ripples, they are not appearing all with equal strengths. These are waves that are overlapping, and some wavelengths appear more often than others. So there are characteristic scales in this noise that we see in this microwave background. In fact, the most dominant characteristic scale is where you see this peak here at an angular scale of about 1 degree on the sky. So these fluctuations are particularly frequent. And this is caused by fluctuations of the baryonic material relative to the dark matter content. And those we can understand very well in linear theory. And this gives us a theoretical prediction, which we call lambda CDM, which provides a remarkably good fit to the measurements of the amplitudes of these noise fluctuations. And this fit you see here on the top, it's one of the really important plots in cosmology, where the data, in this case of the Planck satellite, which is currently the most accurate measurement of the microwave background for all sky, how these fluctuations that you can measure with the angular power spectrum, how they can be explained with this slight blue line here. And that's the lambda CDM cosmological model. And it's something that depends on 6 numbers, which we call the cosmological parameters. These 6 numbers we can't compute through any more fundamental theory at this moment. We can only measure them in nature. And these are numbers like the mean density of the universe, its dark energy content, the amplitude of the fluctuations, and the current expansion rate. And you, of course, would like to determine these 6 free parameters with future experiments even more accurately. They are currently measured to about 1%. And we will also try to find in the future whether this model actually is fully correct, whether the initial conditions that we see here really evolve into the structures that we see around us today. And that's sort of a bit the problem I would like to address in the remaining parts of my talk. So we have the initial conditions. They are in lambda CDM, perfectly known. You can, in that way, also realize them on a, for example, on a computer. And then you can evolve them forward in time. And if you can follow this evolution in time, then about 13.7 billion years later, we should see galaxies like our own Milky Way coming out of these initial conditions. So somehow, the properties of these galaxies are already set by these initial conditions and the astrophysics that governs galaxy formation. Of course, the composition of the universe that you see in the bottom plays a major role, right? We have this cake here is the cosmic energy density today, and about a quarter only, a quarter to a little bit less than a third, a quarter is dark matter. Of course, it's dominating the material content in the universe. We think it's about, it's a lot more, 6 times more so than the ordinary matter, which we call baryonic matter. This is mostly helium and hydrogen gas with some pollution by heavy elements. And then we have 3/4, which is this dark energy fluid. That's the interface. Thanks. And this evolution we can track in what we call in computational astrophysics with large. I think it's this one, maybe. Yeah. We can track with large supercomputer simulations. And as you know, these big computers become ever more powerful. This is very good for our field because we can then actually try to do this computation of the evolution of the universe directly in a big computer. And that's very much the idea of computational cosmology, that you test, does that conjecture really hold up? Does the initial condition, do these initial conditions, together with this quite bold assumption that the universe is filled with these 2 dark components, does that together really yield the cosmic structures we see today? So in that way, that has been, pursued, that idea, over the last 2 decades, 2 or 3 decades even. And I will tell you about some of the results. But before getting there, I want to just briefly remind you what are actually, what are the equations that you're solving, right? For people maybe not directly from the field, just remind you about these, and also that motivates also a little bit why we have to do this on a computer through numerical methods. Because the dark matter is described by the Pozov-Vlasov equation. This is a system of partial differential equations that you see here. The first equation up there describes the phase space density of the dark matter particles. And in principle, this is a very simple equation because it says that the phase space density along every dark matter particle is conserved. The convective derivative of this distribution function f here in phase space is 0 because there are no scattering events between the particles. They are fully collisionless. That's because the dark matter particles, they don't have any residual interaction of any appreciable strength today. They might be weakly interacting, but we think that's so weak that we can safely neglect this here for cosmic structure formation, except, and it's not quite true, in some exotic dark matter models, this is then not valid, but in the standard cold dark matter scenario, there are no interactions of appreciable size. So that's this one equation you have to solve. And then there's still a force entering here, an acceleration, which you see here as a spatial derivative of the potential phi. And these particles respond not to their partners in their neighborhood through scattering, but they respond only through to the collective gravitational field. And the collective gravitational field you can compute by integrating out the velocity distribution in this distribution function. Then you get the particle density. The density, you use then the Pozov's equation to compute the gravitational potential. That's the phi. And that phi couples back to the Boltzmann equation. Now, this is the Pozov-Vlasov system. I highlight this here because I would like to show you that formally, these equations are quite simple. And in fact, you can linearize them, and then you can do perturbation theory and do linear theory. But once the linearization doesn't work anymore, you basically can't solve this system. So in the strongly nonlinear case, it's can't really be solved with pencil and paper. That's why we turn to the computer. So we discretize these systems, for example, through an n-body method, and then it becomes, again, a problem that's computationally simple or conceptually simple. You just follow the orbits of particles. For the hydrodynamics, you have the Navier-Stokes equation of fluid flow. These are written down here. So that's then governing, in addition, the helium and hydrogen gases in the universe that then later are pulled by gravity to make galaxies. And these are also forming sets of partial differential equations, namely, and these are hyperbolic laws of conservation of mass, momentum, and energy. Again, these equations are, of course, well known, but they see very complex dynamics. You all know that turbulence, for example, is a very complex phenomenon that's still not fully understood. But these equations describe, for example, turbulent phenomena. And in the universe, we have incredibly strong turbulence. The Reynolds numbers are larger than anything we have on Earth because the viscosity is very low of the gas. So that's why the gas flows are prone to develop highly turbulent flows. And these are discretized, these equations usually on a mesh, or you can also have much less accurate particle-based technique, or a technique we are using of a moving mesh that I show you later. If you want to follow everything that's relevant for galaxy formation, you have to add additional equations like these. For example, for magnetic fields, you have then to also address problems that are relating to nuclear processes in stars, because they eventually start nuclear burning, and the stars evolve on some time scale and sometimes explode, eject a lot of energy, and so then you have really complex right-hand sides to these equations that treat the explosions, for example, of stars. And you have effects of general relativity close to supermassive black holes. All of that combined, is a very nonlinear, complex mess of equations. And that is something that you would have to solve if you want to study the evolution of the full universe. Of course, that's not possible in full generality. You need to simplify things. And I tell you a little bit about some of these simplifications now first. So that's the composition of the universe today. And historically, the field has often done just dark matter only simulations in the beginning. That's when we replace the ordinary matter also with dark matter. Then you get a universe that's actually dark, filled with dark matter and dark energy. But under gravity, on large scales, the baryons just behave like the dark matter as well. And that gives a useful approximation to understanding what the dark matter is doing. And it's dominating the gravitational field. So you really have to understand that first. Without that understanding, you might as well stop. So that's why this is so important. So I show you here a first visualization of the evolution of this dark matter. If you track it from high redshift, as we say, from this cosmic beginnings to today. And initially you saw a cloud of dark matter that had only little perturbations, exactly those that you see in the microwave background radiation as well. And then as the universe evolves forward in time, you see that structures form out of this soup of matter. And you first get little things collapsing under gravity. They make little halos, as we say, of dark matter that you see here at a pretty early time. And all of this region here will eventually collapse to make one large galaxy at the end. But at the beginning, you see it was actually a fine network of dark matter filaments. And we say that the structure formation process proceeds in a hierarchical way from small things to big things. The small things are formed first because of the initial perturbations. They have a certain power spectrum favoring this. And then they attract additional material, and they attract each other also. That's why they merge to form ever bigger things. And what you currently see is a proto-halo of a large galaxy. In fact, this is a system that has exactly the mass of the Milky Way. So the theoretical picture, how our dark matter in our own galaxy is distributed, is looking like this. Right? So it's actually a large cloud of dark matter, roughly in virial equilibrium, but it's not just a quiescent place where the matter is at rest. Rather, the small substructures that are visible here, they still orbit in the galactic potential to today. And there's actually a lot of effort going into attempts to test whether these things are really there. Most of the dark matter lumps you see here are actually really dark. They're so small that they haven't made any stars. They are really dark substructures, but they might still be detectable by, for example, gravitational microlensing events. And so there are lots of people trying to find evidence that this is really true, or is it not true? And maybe the dark matter halos should look smoother than that. That would then tell us about actually the properties of dark matter, the properties of the dark matter particles themselves. So that's basically what we expect in a simple single dark matter halo. And you see now the evolution has quieted down. We are basically at the end of 13 billion years of cosmic evolution, and that's how the Milky Way's halo would look like today. And the bigger structures you see here, these would be satellite systems in our Milky Way, like the large and small Magellanic Clouds or fornax and so on. There are satellite galaxies known in our galaxy, but only a couple of dozen, not these thousands of lumps that you see here. You can also study the dark matter on much larger scales. Ren, you mentioned this. This is a calculation now, basically 20 years old nearly. This was the Millennium simulation. It was one of the first very large n-body calculations of the cold dark matter. And it shows you the large-scale structure, as we say, the so-called cosmic web, how the dark matter is arranging itself into a finely, an intricate net of filaments that crisscross through the universe, and then they intersect at large nodes of this cosmic web. In fact, this is a galaxy cluster that we see here in the center. The movie here zooms onto this galaxy cluster, and embedded in this cluster, you see little dark matter lumps that are basically the galaxies now that sit in this galaxy cluster. So that's something that we have started to understand in the field about 25 years ago. This is one example, and that was possible at the time already because this computation is so much simpler because it omitted the luminous material, right? Yeah, this is the cosmological structure over scales here of billions of light years actually. So that's something we can understand very well. But actually, we can nowadays understand also the smaller structures here. Actually, this was a recent Nature paper by Ji Wang, where I was a co-author on, where we simulated by zooms down to the smallest dark matter halos that are expected in lambda CDM. These are actually of Earth mass. So you can, over many orders of magnitude, follow that over 30 orders of magnitude nowadays with computational techniques and resolve really everything we expect in the dark sector. So that is a problem that is very well understood from the point of computational astrophysics. We can also change the properties of the dark matter and in principle make it slightly collisional and get the same sort of predictions. So that's something we can understand very well. But I want to now really come to the more interesting problem, more recent one, namely when you do not make this approximation, but we actually would like to simulate the baryonic sector as well, understand how out of the helium and hydrogen that has been synthesized in Big Bang nucleosynthesis in the Big Bang itself, how later on you make out of the stars and how you later on maybe make supermassive black holes that sit at the centers of every galaxy. Now, this is really the full problem of galaxy formation in a sense, right? Of course, you should realize that still the stars and the black holes, they are just the tip of the iceberg in a sense, right? They are, of course, the icing on the cake in the cosmic structures. Underneath of that is all this dark matter large-scale structure that I've shown you, and you'll see this a little bit more in a second. So let's take a look at how we do these simulations. And since I briefly mentioned that that we discretize the dark matter in particles and the hydrodynamics on a mesh, so I want to show this here. This is actually the mesh we are using in our code. It's a special type of mesh. As you see, it's actually moving. It's a moving mesh. It's a complicated geometric construction because it's an unstructured mesh. This geometry that you see here is a so-called Voronoi tessellation. It is created by so-called mesh generating points. You'll see a few in a second here in red. And basically every cell here has one of these mesh generating points. These are just mathematical entities that define the geometry of these cells, right? So around every mesh generating point, the region closest to this point, that's defining its local Voronoi cell. And then the walls between cells, the faces, they are orthogonal to the bisectors of two of these mesh generating points. And then it turns out, why are we doing this? Well, the reason is that you can tie the motion of these points to the motion of the gas, and then the mesh flows along with the material. And that has the advantage that the mesh becomes automatically denser. So in the centers of galaxies, for example, right? Then as you see here, the cells become smaller in the center of a galaxy. There, the spatial resolution then goes up in a smooth and perfect continuous fashion. And this type of method can also follow the motion of galaxies through space, even if it's highly supersonic with ease, while stationary meshes are there, it is harder to avoid advection errors. That's what we're doing. Otherwise, this is really a mesh code. Okay, then some of the physics, I think I can maybe just briefly mention what you're now seeing in the simulation that I'm going to show you. They have not only gravity and hydrodynamics, but they also have additional physics that's treated at some level of approximation in these calculations. The most important blocks you see here, there's one block dealing with radiative processes, cooling, what we call cooling in galaxy formation, namely that diffuse plasma actually emits radiation, for example, X-ray radiation. And of course, that leads to an energy loss in the gas. It cools down. And that process is actually crucial to allow the helium and hydrogen gases to lose their thermal pressure that they gained when they fall into the dark matter halos. And then when they lose the thermal pressure, then the gas collapses further under gravity and can eventually become so dense that stars form. So that's really a key process. That's a process, by the way, that we understand best. But once the gas becomes very dense, it will fragment under gravity, eventually to densities where fusion processes ignite in stars. That's a process that's very complicated. It's not so well understood at all. Here we have a treatment for this, which is much more empirical, star formation, a so-called subgrid model, and also one that's dealing with the non-gravitational energy that you get back from stellar evolution, right? Once the stars ignite their fusion processes, then they shine, of course, they put out a lot of energy. This energy you have to put into your mesh in some way. And later when the stars explode, you again have energy input that you also have to put in. And the whole process of stellar evolution, that's for us a so-called subgrid process. We don't calculate this explicitly. We need to rely on results that other people in the field obtain, working in stellar astrophysics. They tell us basically how much energy a given stellar population will return as a function of age. And the third big prop is basic black holes. And that's they are also believed to be a very important actor in the centers of galaxies. Again, the black holes, they are studying the accretion flow onto a black hole correctly is a very challenging process. It requires general relativistic magnetohydrodynamic calculations that we are not doing here in a full cosmological box. And if you wanted to, even if you could do this, the dynamic range to get down to a black hole would be prohibitive at the moment. The accretion disk of a black hole is maybe the size of the solar system, but you would then have to see this in something like the scale of the observable universe. That is not yet possible with the dynamic range we have. And thirdly, this is something I just want to mention. There are also magnetic fields. There are components of non-thermal pressure, which we also started to include in our more recent calculations. They can also be an important actor. Now, once you include all of this, you then can do calculations like this. This is now showing you the gas in a small region of a cosmological simulation. It's the IllustrisTNG calculation, and here is the gas is visualized in a region, a protocluster region, a region that eventually makes a cluster. What you see is kind of the velocity field rendered, and sometimes, for example, in the bottom and soon on the right, you see also some strange pulsating flows, actually a bimodal outflow coming seemingly out of one little point in this calculation. This is actually because there sits a galaxy with a supermassive black hole that's secreting, and it's, for example, on the right, it's driving a large-scale outflow, a super wind out of the galaxy, and the energy is actually coming from the supermassive black hole that sits here at the centers of these galaxies. Now in a second, you'll see more closely what this actually is. I mean, the protocluster, we blending over to the stellar material that has formed in this forming system. This is basically a galaxy cluster that you see in formation. The white stuff here, these are all stars, and you see that the galaxies that fall into this cluster, they are tidally harassed. Some of the stars are stripped off into tidal arms and shells and ripples that you see in this complex structure here. So that's something we can do, and I'll show you more of movies of that kind to give you a sense of what these calculations can accomplish. This was actually one of the simulations we've done a few years ago now. We call them IllustrisTNG. These are typical cosmological hydrodynamical simulations. They are computed in a box with periodic boundary conditions. You need to simulate an infinite universe, which of course you can't do that. But what you can do is you can put the universe in a box and then replicate it in all dimensions periodically. And that mathematically creates an infinite space that unfortunately has, however, the property that you cannot represent structures bigger than your box, right? It's like a tile that you replicate in all dimensions. But if you do this, then the wall of the box is going away. You are translationally invariant in this box. And so every point then is of an equal footing. And that's very important. Now I want to show you just for fun, again, what you can do with these type of calculations. You see here the dark matter large-scale structure, this time in another color, but it was the same as what you've seen before. Now, this is a property of the gas now, the temperature field on large scales. It's very hot. It's coming from the UV radiation field of the young stars that has ionized here the gas. That's why it's so hot. As we keep zooming in, you see here for example, that is the gas metallicity distribution. These heavy elements cooked in the stars, and they have been blown out by winds into intergalactic space. And as we keep zooming in here, you eventually see the stars. This is actually a galaxy now that sits at the center of one of the dark matter halos. And it's a rotationally supported system. It's looking blue because it has still a lot of young stars. It has ongoing star formation. And this is a system that basically is like the Milky Way, right? So, and it's surrounded by other close by galaxies like in our neutral group. Here we have the gas density now, and in white you see the more the rather dense material that's available for star formation. At the end, you see again a rendering of the velocity field. These bubbles here on top, these are shells, shocks that come about because some of the galaxies have driven outflows. So some material comes out again out of galaxies due to non-gravitational energy injection. And that's something that's really a significant fundamental difference between the dark matter that you see here. The dark matter can only come together under gravity, while the baryons, they also initially are pulled in by gravity into these structures. But at the centers of galaxies, you now have you can tap into the energy of fusion and of gravitational energy and relativistic forms from black holes, and then you can eject material again out of these dark matter halos. This is a realization also that is driving the researchers in the field a lot. What is the cause of, or what type of non-gravitational energy sources are important in regulating galaxy growth? Something that's not fully understood yet. But what our current calculations can do, I've shown you an example, is making these galaxies a bit like, Andromeda, our neighboring galaxy. Our galaxies are not as nice and detailed, but they have, and that's interesting and also significant, they have the right size and also the right stellar mass. They're very comparable to the real galaxies we see around us. So that's, in some sense, an important success, despite many uncertainties, of course. And these simulations, they do not only make a single galaxy, they make hundreds and thousands of them. So you can study the properties of full galaxy populations. And then that's the way we validate whether the simulation of galaxy formation makes sense, whether they can reproduce not only a single galaxy, but the whole zoo of galaxies we see in the real universe. Just an example here, for example, you can then look at plots like these, look at the sizes of galaxies. These are the half stellar masses for the two main classes of morphologies of galaxies, the disk systems on the left and then the spheroidal galaxies on the right. And basically these Illustris simulations, and as well as some others, big projects in the field, they are now able to explain that data, as well as many other properties of galaxies. For example, here is an important one, the color distribution is shown here. This is the distribution functions you see here. This shows the galaxy colors as a function of 6 different spins of stellar mass. So this the smallest galaxies here on the top left, and then you go more massive on the top row and on the bottom, and then the most massive ones on the bottom right. And basically what you see for these intermediate mass galaxies, there are 2 peaks in this bimodal distribution, which is called the blue cloud and the red sequence. So it's a question, of course, for us, why is that? Why do galaxies fall here in these 2 main classes? And what makes a galaxy transition from blue to red? Because actually, for the small galaxies, they're mostly blue, and the big galaxies, they're only red. So this is a systematic change with size. Something makes the galaxies red when they become big. Now, red actually means they're red because they don't form new stars. So the galaxy populations, or star formation dies out. This is called the so-called quenching. Or in other words, galaxy growth stops. So these galaxies stop growing somehow, and we think something must do that, because something which is not gravity, probably, because gravity is scale-free. There's some astrophysics that's doing that. And that's one of the key physics, actually, in galaxy formation, is trying to understand what is quenching galaxies. Now, let me maybe go further and show you how good these calculations are these days. And here is just an example. One can then make mock observations. You take your simulated universe and you basically put a virtual telescope into it and produce, for example, a deep ultra Hubble Deep Field observation. This was a famous observation a few years ago, or actually 10 years ago, more than 10 years ago even. The Hubble Deep Field is one of these two images. I give it away here. The Hubble Deep Field is actually on the left here. That's the real universe, and on the right is sort of the simulated universe. So, you know, from the back there, I think you cannot tell easily the difference. So there are differences. So the simulated universe has clear deficits, but it's actually subtle, right? You have to look hard to see that these galaxies that are simulated aren't quite right? So they aren't quite right, but they come close, right? And that's, for the moment, actually an important thing. You can then also, and it's not only that the galaxy populations come close, also what this cosmic web that dark matter forms. What is studied extensively now in cosmology is how the galaxies populate spatially this structure. Where are they, right? And this is mapped out with big galaxy surveys. Then you can use galaxy clustering to probe how the galaxies concentrate in these nodes. And you can do this with two-point clustering statistics, but also higher order clustering statistics. And when you look at this, for example, the autocorrelation function of galaxies, so here is based the idea, if you sit on one of these nodes, you have a galaxy, and if you ask, you know, how likely is it to find another galaxy at a certain distance, then this distance lies above the probability of a random distribution of the galaxies, because basically of this network, gravity creates concentrations of matter. So if you're sitting on one of these concentrations, it's very likely that another galaxy is in your neighborhood. So that means there's a strong autocorrelation on small scales. So that's well known and has been measured in cosmology a lot. For example, the Sloan Digital Sky Survey, here are correlation functions. The measurements are the black points, again in different stellar mass spins. And we have very accurate data here. So the clustering of the real galaxies is measured very, very accurately in the local universe. And then you can go into our calculations and our simulations and do the same thing. So look at these Illustris simulations and you find, yes, the clustering signal is reproduced actually with quite high accuracy. So that's encouraging. It's not perfect again, but it's very close. And here is a differentiation between red and blue galaxies. They cluster differently. The red ones cluster more strongly. They are higher. It's because they are mostly in the large nodes in the cosmic web, because that's where the massive galaxies live, and they are more likely to be red. So they are therefore more strongly clustered. And also this color difference is reproduced to first order. And I've already shown you that these modern calculations, they can really be, you can ask many, many questions about them. You know, when you want to study galaxy formation, you can ask also how did a particular galaxy form in time? This is something you cannot easily do in observations. In a simulation, you have the opportunity to actually track the temporal evolution really accurately. That makes these calculations very useful. That's why really hundreds of papers have been written by them about them in the field already. Now I want to say something briefly, a couple of minutes, I hope I still have, about maybe modern challenges. One first on the challenge of cosmology. This is a satellite mission that just started taking data recently, the Euclid satellite, that's trying to map out several billion galaxies with the target to use galaxy clustering and also weak gravitational lensing to study the lower redshift universe with so high precision that you get clues about the dark energy. Is it this is one of the most fundamental puzzles in physics. We don't really, we have, there are conjectures what this could be. The standard assumption is Einstein, cosmological constant in Einstein's field equations, but field theoreticians, they are not really very happy with this. There is the hope that one finds a unified theory between gravity and quantum field theory, for example, or some higher order, higher dimensional theory of gravity, string theory, whatever, that gives possibly an explanation to the dark energy. That isn't yet there, but to get further, we need experimental input. We need to find more information about the properties of dark energy. And this is one of the missions that targets this. And there are many other ones that will do similar things in the next years. And if you follow the press, There's been a claim by the DESI experiment just last week that they detected, with some 2.5 sigma or some 3 sigma, some difference to cosmological constant. So there are beginning signs that we may be on the verge of discovering something new about dark energy. But to interpret these data of these missions, you actually need really big simulations. That's also new because the systematics is really difficult to understand otherwise. You need very large simulations, and they need to be in very large volumes. And the calculations I've shown you so far, even though they are already substantive and contain a few million galaxies, they're by far not big enough for these cosmological scales, in particular for what's called baryonic acoustic oscillations, which provide a standard ruler to measure the expansion history of the universe. So we need larger volumes. And in this new recent simulation project, we've done that. We reached now a volume about 1,000 times larger than our previous biggest hydrodynamical simulation, TNG 300. And with this, you can then map out also in the galaxies, the large-scale structure. This is coming out of the simulation, for example, the distribution of the galaxies. You see that on the right is an enlargement of this large so-called light cone that shows us basically the galaxies, how they look like. If you look out to space about to redshift of 2, this is more than 5,000 megaparsecs in the past. So this is something like 15 billion, it's a good chunk of the observable local universe. And you see that the galaxy distribution in this background image becomes thinner on the top. That's because you're looking out so far that the structures haven't grown so much. There are just fewer galaxies. And you can also only see the brightest ones back there, right? And these effects that the sampling, of course, goes down in observations the further you look. That is something we need to very accurately model with these simulations. And we now can do that. And with this, you can then, for example, measure the baryonic acoustic oscillations. We've written papers about this, about various systematic effects and so on. I spare you the details. The other interesting thing you can do is you can turn to another very important component. These are neutrinos. So we know that that's actually what we know. There is a dark matter component, which is neutrinos. They interact really weakly. They are out there. We have a large neutrino background. What's not known is there's a lower mass limit to the neutrinos. We think they are not, they don't have zero mass. That's known now from particle physics. There's a lower bound of some mass of about 40, 50 milli-electron volt. But then how massive they are is not very well known. And it's very difficult from beta decay and so on experiments to measure the neutrino mass directly in particle physics. That's attempted. But what I'll show you is also interesting to consider what do they do in cosmology, because for masses of that size, about 100 or so milli-electron volt, that's the suspected mass range, maybe 200 milli-electron volt even. For this mass range, the neutrinos will be starting out at a high redshift, being almost at relativistic speeds. But with the expansion of the universe, their velocities get redshifted, and then they become, as we say, non-relativistic at some point. So their velocities become so small that they start to respond to the cosmic structures that have formed, and they are feeling basically now their gravitational field, and they start to clump as well. That's what you see in this light cone here on the top. That's the neutrino density field. We are in the center here, and in both directions, you're basically looking out into the past, and also to high distances. And you see that here at redshift 2 on the left, the neutrino density field is almost uniform because the neutrinos are still relativistic for the most part. But then towards late times, they start clumping and they respond to the structures we see. And for example, to large galaxy clusters, that's here an enlargement. And this enhances the density contrast of these structures. And the neutrinos contribute about 1% to the dark matter in this case. So they are, so we say, a hot dark matter admixture. So that's something we can simulate. And again, we can study in cosmology now the effects this has on structure growth with high precision, and with this constrain the neutrino mass. So that's something that hasn't really been successfully done, but there's a real prospect now that in cosmology one, with the upcoming accuracy, that one even has a handle on the neutrino mass. So that's quite exciting, actually. And this is measured by effects like this. The neutrinos, then they damp the matter-power spectrum on certain scales, and one can also then link this to and compute this for the weak gravitational lensing effect, and understand from the simulation not only the systematics in weak gravitational lensing, which is so-called intrinsic alignment, that we can do with our very large volume now with the required statistical precision. I just show you this, that we can now compute basically the systematic perturbation of introduced to weak gravitational lensing. The weak lensing introduces so-called E-mode distortion in the shapes of galaxies. If you have a big galaxy cluster, for example, then galaxies that are further away, they will see their shape distorted in a tangential direction by that mass. It's a very weak effect. You would not see this. You could not tell it that on an individual galaxy. You can only tell that happening statistically. But the intrinsic alignment effect will actually counteract this through an intrinsic radial alignment. That's something we can measure with these calculations with very high precision. Yeah, and these are also weak gravitational lensing effects. And we need to understand how the neutrino effect, which you see in the white line, there's a 5% damping of the structure for standard neutrino masses. And on the very right, you see the impact of the black holes on the neutrino signal. And that's something that I think I don't really have the time in this talk to discuss in any detail. Let me maybe just give some motivating slides before I close about this impact of so-called, the main actor, the main two actors of this non-gravitational energy input are the supernovae on one hand, that I alluded to a few times. Those supernovae, they impart about 10 to the 51 erg per supernova explosion. But a quasar, which is an accreting supermassive black hole, that releases about 10 to the 60 to 10 to the 61 ergs during one activity phase, right? So you have 1 billion supernova explosions right there, just from one episode of quasar activity. And then the question is, it's very important for us to know what's more important as a source of energy. Is it the supernova explosions, or is it the liberation of the energy in quasars that is the energy liberated by accreting black holes? And turns out that they are about equal. Both of them release about a similar amount of energy over the history of the whole universe. That's also, in a way, why you can already see that there need to be both included in serious calculations of galaxy formation. But what we don't understand very much yet is how does AGN energy actually couple to the halo gas? And here Renyu just proposed a new model for that, which is a possibility that conjectures an interesting alternative to more traditional conventional thinking. Okay, and yeah, so I think just show you one of these ideas is basically that when two galaxies merge in this hierarchical process, you see this in this galaxy merger calculation, which is quite old. Then what you have initially are two star-forming disks. When they merge and they make an elliptical galaxy, you also funnel a lot of gas to the embedded supermassive black holes, and they shine as a quasar. You see in the illustrated with this yellow flash of light coming out there, and this quasar activity releases then this enormous amount of energy in a very small spatial region, and it's blowing away the residual interstellar medium like an exploding pressure cookpot or so. And then you end up with a galaxy that turns red because the star formation has been quenched. So the activity of these black holes is one possibility to quench star formation. So I should come to a close, I think. So I just want to show you this effect once more in a little movie. The importance of, this is from an older test simulation or from an older calculation, not IllustrisTNG, it's Illustris. This is now also quite old, but it shows you a comparison on the left of the gas evolution And both left and right, on the left one, there is no extra physics included, no radiative cooling, no black holes. On the right, you have the whole physics, including black hole activity and supernova explosion. And you see how different this is. The left, you get heating in these concentrations. This is just from hydrodynamical shocks. Those are heating the gas to zero temperature. But on the right, you have cooling. That's why much of the gas gets cold, blue. And in the concentrations, you have these explosive outflows now from the black hole activity. That illustrates just how important these small-scale physical processes and how they affect the large-scale distribution of material. This makes this problem really a very difficult one. You have a so-called multi-physics, multi-scale problem. And multi-scale here because the small scales act back on the large scales. The tiny stars and the tiny black holes, they affect the large-scale distribution of material. And this back reaction is coupling many different scales together. That's why galaxy formation is such a nonlinear and complex phenomenon. Yeah, I will leave it with this. This is just my next to last slide. Here a couple of images from our simulations. Maybe I've been too optimistic and have advertised the successes too much. I want to caution against that. So I think it's true that these recent simulations have made great progress in reproducing many internal properties of galaxies. So I think we really have, I would say, kind of a standard model of galaxy formation that is sort of at the level of a pretty detailed sketch actually working. But here and there are some things we don't really understand, but we have sort of a background model. This wasn't really true 20 years ago. We were much more at the very beginning. So, and you might ask then, do we understand galaxy formation now? Is there anything left to do? And, I think, unfortunately, we don't really understand it. There are a lot of things that go into these calculations as strong assumptions. And, is there anything left to do? Yeah, a whole lot. And I'm sure many of you here in the room, at least astronomers and astrophysicists among you, and I see lots of young faces, I think you will be the people who will actually finish this off. Yeah, and so I'm basically at the end of my talk. I wanted to give you a bit of an overview of recent hydrodynamic cosmological simulations. They successfully form galaxies within the lambda CDM cosmological model. We can also study alternatives to this, but these computations are expensive to do, so you cannot really, unfortunately, do very many of them. That's something that's changing in the future. We'll get more computational power, of course. And I've given you only a few slides on results actually, but you believe me, there are literally hundreds of papers that have compared the galaxy populations across many different data, and the level of success is quite stunning overall. There are also tensions at many places, but I think overall the success is maybe much better than we might have expected. But recently, especially with, I didn't really talk about this, but the JW Space Telescope has discovered very high redshift, very massive galaxies very early. Those are not really reproduced, for example. This is one of the tensions we have, right? So we need to think about the very early universe. And I've also briefly showed you our new MillenniumTNG simulations. They include now massive neutrinos, and they make very important cosmological predictions. For mega galaxy surveys, like Euclid as an example. LSST and others are also forthcoming. Thanks a lot for your attention.
Okay. Questions? Given that lambda CDM seems to explain structure formation so well, is there a room for the time-dependent dark energy proposed by DESI? How would things change?
Yeah, there's definitely room. Things will change very little. The reason is that the time-dependent dark energy or dark energy in general here comes in only very indirectly through the Hubble rate, right? So all you get is a very small change in the late time expansion. And that is very subtle. So there would not be any huge change no qualitative change whatsoever. It's really a small quantitative change that you would get at most. Yeah.
No questions? So I just want to know, is there some artificial intelligence such as machine learning used in
Yeah. So yeah, the quick answer is no. No, there's no machine learning at all in this, at least so far. I'm glad that you didn't ask why are you still bothering doing this and why aren't you just using machine learning? Because sometimes I'm asked about that. You know, can these calculations be replaced by machine learning? I don't think so, because you need, even for the best machine learning algorithm, you normally need good training data. So at the very least, you need good training data, maybe. But these new methods could be useful to generate additional realizations potentially. It's also discussed whether you can somehow use them to accelerate certain parts of the calculation. I'm not too optimistic about them. They are very much useful to so what I mentioned was you cannot simulate very many of these detailed models, but what machine learning, for example, can help you with is for these cosmological applications, what you will ideally would like to know. I was just asked is what happens if you slightly change the dark energy, right? So, or what happens if you slightly change omega matter, for example, etc. So, and this is what you need to do in the so-called inference problem. If you have some data and you want to compute the posterior likelihood of distribution function of your cosmological parameters, you actually have to simulate many different models. You need to be able to predict the outcome for any combination of these input variables. The idea is that you run a few simulations for different, choices of these parameters, and then you train an emulator, and with that emulator, a machine learning technique, you can then basically very quickly recreate intermediate values, right? So that's where machine learning is used already quite successfully.
Okay. I wonder the formation of the supermassive.
Yeah. Yeah, so we actually do get this as well. I mean, some galaxies merge, right? What happens is the galaxies merge. Sometimes the galaxy is disrupted. Then you bring in another black hole, a supermassive black hole. This will sink into the center by dynamical friction. And then eventually the question is, how do these two black holes now find each other, right? To make a binary, they would already have to come relatively close. So the initial thinking is by dynamical friction, that's relatively well understood. And then later they can eject stars that also brings them close together and eventually they form a binary that dance around each other. And then the question is, how long does the binary hang around until it can merge? That's a really interesting question, because for a while it was thought that they might got hung up basically because they eject all the stars in the environment and then that dissipates and close together. But then the stars that can reach them, they are gone, and then then it takes forever before they merge. Nowadays, one thinks that because of the triaxial potential and because of gas that's also around, there's always kind of enough dissipation to sink them further to the point that eventually the gravitational wave emission takes over. That's the final actor that brings them together. So, and we think this, the rate, so this will be very important to understand this for LISA and for future experiments that will be sensitive to gravitational waves, very low frequencies of mergers of supermassive black holes. Like we would see them to the edge of the universe, and we can use these calculations to predict the rates. They are similar to the rates of mergers, but if a binary stays around for a long time, then a third black hole can come in. And when you have a triple or quadruple, the interactions are very dynamic. Then you can eject some of these black holes back out, and then they might never come back. They might hurtle through space. And so there are very interesting, open questions about the dynamics of multiple black holes interacting. And also, when you then have a merger, then you emit gravitational waves. A lot of, it's a huge event, and the this emission is asymmetric, there is a recoil, the remnant supermassive black hole will be kicked out of the galaxy center a little bit, and if it's only a little bit, it will come back after a while. But if it's a lot, it might also leave the galaxy. These are all very interesting questions that people study at some level, but there are many, many questions open.
Any other questions? I have a question. So, MillenniumTNG, in order to sample the neutrino mass, can you do a lot of them?
So we have done 3 at the moment only. Unfortunately, yeah, we have done basically 0 mass as and then 100 millielectron and 300 millielectron volt. So then we have at least some measure. Okay, how but we would of course like to do more, but it's difficult. It's expensive, right, to do more of them. Yeah. So, but
it's AI thing, like doing interpretation for you.
Again, yeah, it could. I mean, for a similar argument I made earlier, it would, yeah, that would be, you would ideally, maybe 2 masses is not quite enough, but with a 3rd mass, and then you get, I think you could train, and you could then smoothly, you can then interpolate, and you would not have to run 10 or 20. A few probably would be enough, yeah, to get it.
And then, what do you think of baryons physics?
Yeah, the baryon physics. So yeah, it depends on what scales you look at, and the clustering measurements now that are done, they are probing into scales where the baryonic effect is seen. So basically, the suppression of baryons in large structures, right? So preventive or ejective feedback modifies the matter power spectrum on scales that are accessible by weak gravitational lensing. And the cosmologists, these effects are they are nonlinear, and you either have to throw away the data because they are too poorly understood, which is to avoid. So that's what some cosmological experiments need to do. But if you can include these scales, you have 5 times more constraining power in principle. And so it would be very important to understand better the level of, for example, how the baryon fraction in large clusters is a key input quantity.
I have 2 questions about the magnetic field in galaxy formation. The first one is, do you think there is an important role of magnetic field in galaxy formation? The second one is, how do we put the speed of magnetic field in these initial conditions?
Yeah, these are very good questions. So I can tell you what these calculations have done. So we have simulated here so-called ideal magnetohydrodynamics, which is meaning the field is always flux frozen into the gas. And in this ideal magnetohydrodynamics, which is a good approximation for much of the gas, not everywhere, but it's a good approximation in general. But there you can amplify magnetic fields by shear flows and by so-called dynamos, if you have a turbulent dynamo, quite efficiently actually. But you have to start from somewhere. You need a so-called seed magnetic field, and we put this into the initial conditions just with a constant, very low field strength. Right? But this is sort of a very ad hoc assumption. There are models that predict that you create a primordial magnetic field. So that's basically what we used here. You can also create so-called, there's a Biermann battery and other type of plasma physical processes that create by charge separation a small weak field. Also stars do that, for example. When a star explodes, it spreads out a little bit magnetic field. If you then have a turbulent dynamo, this field can be picked up and further be further amplified. So that's one way. Also in accretion disk, you can amplify magnetic field strongly. So there are these so-called dynamo processes. So we included a uniform magnetic field, meaning that the magnetic field is initially very, very big, 10 to the minus 14 Gauss or so, what we used. But inside galaxies, there's enough turbulence to support a small-scale dynamo. So in the galactic disks, the magnetic field is quickly amplified to micro-Gauss levels. So in the interstellar medium, this is basically a star-forming disk, we have magnetic fields that basically are growing to equipartition with the thermal pressure. So we then have in our galaxies, the magnetic field is then important. But once once the magnetic forces become similar to the thermal pressure gradients, then the dynamos saturate and they stop, right? So you can get basically naturally so-called beta value of unity. You get equipartition between magnetic field and thermal. That we do it in galaxies. Now, what you also ask, is this important now for our galaxies? Yes, I mean, it's not making a huge difference for the stellar mass we are forming, because the interstellar medium is, through this magnetic pressure, made slightly less dense. So that's reducing a little bit the star formation rate in the beginning, but then you accumulate more gas, and at the end of the day, you form roughly the same amount of stars. But it also influences, interestingly, the growth of the magnetic field, the growth of the black holes in an interesting way, because of this additional magnetic pressure. So in our case, so far I would say it makes not a huge difference in our calculations, but we have not yet all the relevant physics related to magnetic field included. Right? We'll have to see this in the future. So basically, the impact we have right now is such that we create magnetic fields in all galaxies of microgauss level in the center. That's roughly also what's observed. So in equipartition, but we do not yet, we don't prevent gas, for example, from coming in, because our magnetic fields are extremely weak everywhere outside of galaxies.
During the process of the whole simulation at a very early stage, do we have any evidence about the primordial black holes?
Evidence, yeah. So that's an interest. So primordial black holes, I'm wondering whether you allude also to the possibility that dark matter could be partially or fully primordial black holes. So this is an interesting idea that has been seeing some kind of new resurrection, because it has to do also with the fact that we haven't found the dark matter particle yet. And there are actually field theories that quite naturally predict also a creation of a spectrum of black holes in the early universe, and so-called primordial black holes. They're basically coming out of the Big Bang in a sense, right? And if they are light enough, you would not be able to detect them. Right? For example, if they all are of mass of asteroids, there is no known observational constraint on this. You could hide all of the dark matter in primordial black holes with asteroid-sized masses, right? So that's a possibility. Now, if the spectrum of these primordial black holes is much bigger, then, so if you can't have it, in solar mass stars or so, then you would have too many microlensing events and so on. So there are certain constraints. Yeah. But if you allow for either really light ones or for a distribution function, then you can represent almost all the dark matter, or a fraction or all of the dark matter through primordial black holes. So there are now people who look for further tests, right? There are already constraints from critical lensing that you cannot do you cannot hide some primordial black hole masses, but there is a spectrum that you can have. And if they're too light, then they're evaporating by Hawking radiation, but there's a whole spectrum that's possible. Yeah.
It's a big plus for the speaker and the tongue. Thank you.
Oh, sorry for this noise.
Yeah.
Yeah, just I think
Not a problem. Thanks.
Let me check if the car's here.
Yeah. Yeah.
Thank you, Professor Springel.
Yeah.
You can close it.